Okay, let's jump right into this. We are looking at a wildly fascinating paper by Kyle McLean-Smith called The Cycloid Logarithmic Bridge. In this explainer, we're tackling a massive bottleneck in quantum state machines, and we're going to do it by completely pulling apart abstract math from physical reality. This paper proposes a totally new way to look at how we compute, moving us away from endless, infinite math loops and firmly grounding our algorithms in actual, uncollapsed physical hardware space.
Here is our roadmap for the explainer. We'll quickly hit 1. The spatial confusion, 2. 1D mathematical engines, 3. The 2D physical canvas, 4. Tracing the macro column, 5. The golden quark, and wrap up with 6. The copper phase shift.
Let's kick things off with Section 1, the spatial confusion, map versus territory.
To start, we need to establish a major pitfall in how we currently model state machines. The problem? We are constantly mistaking the map for the territory. According to Smith's research, a massive source of confusion in spatial state machine modeling is the implicit collapsing of 2D geometric tiles into a single 1D scalar number. Basically, we take a physical shape with a real width and height, we multiply them together, and we just slap the label area on it. But doing that completely erases the physical boundaries. Think of the 1D mathematical engine like a volume knob. It's just a dimensionless multiplier telling us how much to change. But the 2D canvas? That's the actual uncollapsed physical speaker hardware you're adjusting. If you just obsess over the volume number, you entirely lose sight of the physical shape of the speaker itself.
Moving on to Section 2, 1D mathematical engines.
Let's isolate that volume knob for a second and look at the pure math ratios that tell our system how to scale. The paper introduces a core 1D scaling ratio called the forward decay factor, or lowercase d. You calculate this using some basic right triangle trig c minus b over a, which happens to equal the tangent of the half angle. This spits out a value less than 1, meaning it drives inward scale contraction. But here is the really fun part. Look at the variable b. The author gives it this incredibly specific, almost sci-fi name, the governance shadow. Tuck that away in your mind, because that governance factor is literally going to cast a shadow on our physical hardware in just a minute.
And of course, the flip side of decay is expansion. Meet the reciprocal multiplier, uppercase D. This guy does the exact opposite of our decay factor. It's calculated as c plus b over a, which gives us a value greater than 1. This pushes the geometry outward, expanding the field. So together, D and D act as our pure 1D mathematical engines. They are simply dimensionless scaling ratios dictating how many times a coordinate field should expand or contract.
Section 3, the 2D physical canvas.
Here's the catch, though. Numbers don't just compute themselves in a void. They have to run on physical hardware. This map perfectly illustrates the distinct spatial progression of our hardware tiles. This right here is the 2D physical canvas of uncollapsed tiles. Notice they aren't just arbitrary points sitting on a number line. Every single tile in this D_n sequence is defined explicitly by a physical horizontal width and a vertical height. The paper is absolutely adamant about this. We have to track that width and height independently prior to doing any scalar multiplication. We have to respect the geometry. Let's see this in action with Section 4, tracing the macro column.
Let's zoom way out to the largest physical tile in our sequence to see how this 2D uncollapsed hardware canvas behaves. We're starting at step -1, zooming outward to the D_-1 tile. Here, the base width is exactly 1, but that vertical governance, remember that variable b? It adds upward. It stretches the height to create what is essentially a golden macro column, which scales outward mathematically to the golden ratio, sitting right around 1.618. It just expands outward past our peripheral vision into unknowable macro space.
Section 5, the golden quark.
Now, stepping inward from that macro space, we land at our baseline at index 0. This is the D_0 tile, a baseline capping block sitting right above our geometric right triangle. The absolutely crucial takeaway here is that this first quark has 0 governance shadow subtracting from its width. The transverse width stays perfectly untouched at 1, while the height contracts to our decay factor d. Based on the author's normalization, this specific tile is locked flawlessly to the golden ratio half angle. It is pure, unshadowed, physical hardware space.
Which brings us to Section 6, the copper phase shift.
So what happens when we zoom in even further? Let's quickly recap our steps. We moved from the massive macro column at step -1 into the perfectly unshadowed baseline of the first quark at step 0. But the second we take that next step, zooming into the second quark at index 1, the physical canvas is forced into a major transformation. That mathematical governance shadow we've been talking about, it finally bites into the physical width.
Just look at the uncollapsed dimensions of this second quark. The height is still decaying by factor d, which we expect, but the width? The width is no longer 1. As the spiral turns inward, that governance factor casts a dual-sided shadow right across the base. So the width actually physically contracts by the expression 1 minus 2bd. We are officially no longer just dealing with a simple linear 1D height change. Our actual 2D hardware width has literally been eaten into.
And that brings us to what is easily my favorite quote from the whole paper. Because this governance shadow bites into the physical width, the author states it is, quote, executing a cubic phase shift that transitions the scalar area from gold to the metallurgical copper reciprocal. I mean, that is basically mathematical alchemy. By keeping the width and height uncollapsed, the math definitively proves that simply stepping the geometry inward cubes the golden ratio. We physically shift the hardware canvas straight from a mathematical state of gold into the mathematical coordinate for copper.
To tie this entire journey together, look at how this plays out. When you multiply the physically accurate, uncollapsed width and height together, you get your scalar area. Because the width physically contracts alongside the height at step 1, the area doesn't just drop to d squared, it drops to d cubed. Preserving those uncollapsed physical dimensions gives us this incredibly beautiful, odd integer power sequence for the total area. We drop from a power of 1 for gold directly to a power of 3 for metallurgical copper.
So, what is the ultimate payoff here? Why does separating our 1D abstract algorithms from our 2D physical hardware actually matter? Well, the paper concludes that if we define these geometric tiles as the exact area needed to seal a geometric system, basically letting the physical hardware naturally dictate a bit-perfect stopping point instead of letting abstract math loop into infinity, we can achieve a 74 times reduction in computational energy. 74 times! If we can hit a bit-perfect deterministic hardware halt simply by respecting the uncollapsed 2D physical geometry, instead of blinding ourselves with 1D scalar numbers, just imagine what this could do for the massive energy demands of modern computing. The real question is, are we ready to start computing with the territory instead of just the map?